Over the next 3 videos, we're going to be looking at outlier models. When we talk about outlier models, we're talking about looking for anomalies, unique things that are out of place. This might be identifying spam emails. This might be identifying fraudulent activity. It might be identifying particular data points that just seem out of place that we need to investigate further. So let's look at some different types of outlier models. We've actually talked about some of these already, so it's a good chance to review what you know. So for example, can you list off the top of your head the different classification models? I flashed them up on the screen, but in the videos we went through a number of them. So what were they? And which one was used for finding anomalies, for outliers? Well, when we did classification models, we talked about support vector machines and how they could be used for finding outliers by simply having one class. And so the support vector machine would identify things that didn't belong to that one class. If we're looking for anomalies, outliers when it comes to text, like spam emails, we would use the naive Bayes method, specifically one that's called multinomial naive Bayes, because that allows us to analyze text. And here, by having one class in our classification model, we can find those that don't belong to that class. Now, we can also do cluster analysis. So before I turn the slide, can you name the different types of cluster analysis that we've discussed and which one we use when we're looking for outliers or anomalies? Well, when we do cluster analysis, remember, cluster analysis does not have a labeled data, whereas the classification models, we have a label, so we can determine how accurate we are at identifying the outliers or anomalies or fraud. With cluster analysis, we're looking for behavior that's outside the norm, and for that we can use the DBSCAN. Okay, so what we're going to do in this video is we're going to look at DBSCAN. And in the video after this, we are going to look at Benford's law. So Benford's law is similar to Zipf's law that we talked about when we did our text mining and analyzing text. With Zipf's law, we look at how efficient communications are because common words are going to appear twice as often as second most common words. And so you get this exponential decay when it comes to words to indicate that we have efficient communication. Well, Benford's law allows us to look for fraud in numbers because it follows that same exponential decay. And so we can look at the numbers, the first digit of numbers for, let's say, some financial reports, and it should follow Benford's law. It should have that exponential decay. Otherwise, maybe a bunch of those numbers have been made up. And in our last video in this series, we're going to look at forecasting models. And here we're going to create a forecasting model using Profit, which is Facebook's model for modeling when there is seasons, when there are difference between day during the week and the weekends. And we can use that to identify anomalies as well by looking at how far we are away from that trend line. And so we could look at, for example, any data points that fall outside of 2 standard deviations, going back to the empirical rule here, where if something is more than 2 standard deviations out, that should only be about 5% of your data. And we could look at 3 standard deviations, that's 99.7% is within. So we could classify anything outside of 3 standard deviations as a potential outlier, and that's designating less than 1% of our data is likely an anomaly. And then we go and investigate those data points to see what's going on there. Is it an error in typing in the information or collecting any of the information, or is there something unique that we need to address? So in this video, we are going to look at DBSCAN for anomalies, and in the following 2 videos, we'll do Benford's law and we'll do our forecasting model with Profit. All right, so let's go do this. For outliers, we are working here in this particular Python notebook, which you can find at drstephpowers.github.io/BIA. And we are working in the book here that is called Outlier Detection under Predictive Analytics. we're trying to predict what's going to happen. So we're trying to predict what, in terms of our models, what is going to be out of the norm. And we're really just, it's in this section, not so much because it's predictive analytics, because we are applying the knowledge from our forecasting models, from our cluster analysis. We're taking all of that and using it for application. All right, so let's dive into that. All right, we're going to use the credit card database for the DBSCAN fraud detection. Oh my goodness, I gotta spell correctly here. This database is a large one. We are actually going to reduce it down because Google Colab only can allow so much bandwidth, and because it's free, it only allows so much processing power before you have to pay money to use Google Cloud instead, or you do this outside of a cloud computing service on your home computer. So it is a large file, which means you will need to actually download it here from our large data sets. You can see it says credit card data set here. When you do that, it's actually just downloading a copy from my Google Drive that you can find here. You can also find this this document at Kaggle as well if you want to sign up and download from them. To get access to it in case you don't know me and you don't want to download something from my Google Drive. Totally reasonable. But it's a large data set. So we want to download it and then you want to put it into your Google Drive. I'll put the link to the Kaggle into this file here. But in order to access it, once you have put it into your Google Drive, you will need to mount your Google Drive once you have opened a copy of this workbook and saved a copy into your Google Drive, then you can use it to access your own files. So we'll load in this credit card here. And as I said, it's a very large file, so it is a little on the slow side for loading. When we look at this credit card file, you can also get this credit card file under Google Cloud. So if you want to use SQL to export it like we showed in a previous video, you can get it that way as well. All these public data sources, they're in lots of different locations, so you choose. You can export it from Google Cloud. All right, so you can see here that what we have is 28 different variables that are a bit disguised here. So we have 28 different variables used related to credit cards. And we are trying to look at these different variables and see if we can identify which of these transactions are fraudulent. The actual database here has 284,807 different rows of transactions. That's a lot. We are going to first just kind of scramble here the data set just in case if we only take a subset of it. The concern, of course, is that, you know, the first 10,000 are not fraudulent and the next 10,000 are. We don't want to take 10,000 and then get none that are. So what we'll do here is use this frac equals 1 sample. Frac equals 1 is it basically just rearranges all the rows. So we'll do that. And then what we're going to do is we're just going to take the first 5,000, and I'm doing that because I'm on Google Colab, and there is limitations for our free version here in terms of our cloud computing. When I do a lot bigger, then what happens is when I start to do the model, it runs for 10 minutes and then craps out because it's exceeded the amount of processing power that I'm allowed for free. All right, so we'll simplify our model, and then we're going to use cluster analysis to detect the fraud. We're going to use DBSCAN. So here's a chance, maybe pause the video and actually build the DBSCAN model just like we learned about in our previous video when we talked about cluster analysis. So applying to clusters here. Remember how we decide then how the hyperparameters for our DBSCAN. So we actually use nearest neighbors. So sklearn.neighbors, import nearest neighbors, and import matplotlib.pyplot_splt. That's going to help us set the hyperparameters. And then we're going to use sklearn.cluster import DBSCAN and sklearn.preprocessing import standard scalar, so we can standardize these variables, although it looks like they might be already, in order to run our cluster analysis. So this big data set here has a couple columns we don't need, so time and amount and class. Okay. So if we're simply trying to detect the fraud from this data set as opposed to predict the amount, then we would ignore those columns, okay? Now, in this case, what we would do here is we would want to remove that time, amount, and class columns. And so to do that, we learned how to do that when we learned about how to manipulate data early on when we were first learning about how to do Python in our early videos. And what we do is we make a list here, time, amount, and class, we would remove. So we want to remove those. So we're going to actually take that table and we're going to use the drop function here to drop the names of the variables that we have listed. And so because we want to drop the columns, we do axis equals 1 and we run this. You can see that this is instead we have, or now you see that they're gone, right? Okay. All right. So then what we want to do is if we are using our k-nearest neighbors to find our hyperparameters and we're using DBSCAN, we need to standardize these variables and we need to convert X into an array. So it has to be the proper format for this. So first thing we do is create an array using NumPy as NP. And then we use our standard scalar to fit and transform that. Then we're going to use k-nearest neighbors to find the hyperparameters for our DBSCAN. And recall for the DBSCAN, we have our EPS and our minimum samples. So our minimum samples are going to be the same here in our n nearest neighbors. And we're essentially going to be doing 2 times the number of variables. Well, we have 28 variables here, so 2 times that is going to be the number of nearest neighbors as we try to figure out what the appropriate number is for the EPS parameter in our DBSCAN. So we're using nearest neighbors with 2 times 28. We're going to call the model, fit the model, and then output information here. So this is the same code we used when we did DBSCAN in our cluster video. This runs a lot faster when I have a much smaller data set. Oh my goodness, it was going forever. 10 minutes and then conking out. All right, so what we can do is we can pull the distances from this and we can then plot those distances. Remember, we are looking for the elbow, the turn here, to help us figure out what the appropriate EPS are. And so we can see that's probably right around 5. So when we do our DBSCAN model, our EPS are going to be 5 and our minimum samples is going to be 2 times 28. We're going to call the model, we're going to fit the model, and then we're going to get it to give us the labels. Okay. Well, now we have labels, a 0 label and a 1 label. So in order to see this, what we need to do is, we'll start on 0, 1. Remember with DBSCAN, a -1 label is going to be the outlier or anomaly. So let's actually take a look at this. So 0 is part of the main group, -1 is an outlier. So what we're going to do is from Seaborn, we're going to import scatterplot. We're going to import matplotlib as MPL. We do that, right, to make these dots bigger. You could leave them as is if you want. And we can import matplotlib.pyplot as PLT for the scatter. So we're going to do scatterplot. The x-axis is going to be just one of the variables. So I could pick, for example, variable 3. And maybe the y-axis variable 4. And here I'm going to color code based on these labels. And we can do palette equals deep. That's going to be blue and oranges. You can change that. And we can make the x-axis match if you wanted to say variable 3, variable 4. We can then create that to look at. So then we can start to identify those particular data points that are seen as anomalies, as outliers. And so we can see, for example, with variable 3, that once we get below a -5, we're detecting an anomaly. So taking this back to our discussion about turning cluster analysis into business decisions, if you can create a line, a vertical line or a horizontal line, then that rule can help you then identify clearly outliers in the model, flag instantly fraud. So if this is credit card transactions, instantly flagging fraud would be if whatever this variable 3 is Anytime it's less than -5, that should be flagged as a potential issue. And we can go through and look at, I haven't gone through more than just a couple of them, but we could go and look at 5 and 6, for example. And so just like in our business use case, we start to look for, can we make clearly identifiable business rules in order to identify these outliers? So for example, with variable 4, if it's below -4, then that flags as an outlier. So we can start making these rules to help instantly identify problematic cases. In our next video, we'll look at other methods for detecting outliers, including Benford's law and then using regression.